Hello again. Today we're going to continue with our study of inverse trig functions. We're going to start by evaluating some quadrantal values. So remember with an inverse trig function that you put in a trig value and your output will be an angle. So you want to know which angle has a trig value of -1, a sine value of -1. So this -1, we can't draw a triangle for that with a sine of -1. So we need to think about the graphs of the functions. So then we ask ourselves, this sine graph, what angle has a sine value of -1? So remember the sine graph starts at 0, 0 and then goes up at pi over 2 to 1. At pi it hits 0, and then at 3 pi over 2 it hits -1, and at 2 pi it goes back to 0. So at 3 pi over 2 it hits -1. But remember that 3 pi over 2, or 270 degrees, is not part of the outputs for our inverse sine graph. Remember, the outputs have to be between 90 degrees and -90 degrees. So let's back up a little bit on our sine graph. If we continue the sine graph to the left, we would hit -1 on our y value at -pi over 2, or -90 degrees. And that falls within our range of angle outputs for inverse sine, from 90 to -90. So we can see that -pi over 2 is an acceptable output. -pi over 2. Second up, inverse cosine. Inverse cosine of -1. So which angle has a cosine of -1? Let's look at the cosine graph. Pi and 2 pi starts up at 1, drops down, comes back up, and so forth. Continues there. So which angle has a cosine of -1? So we see the cosine is at -1 at an angle of pi radians. And we check, is pi in our acceptable range of outputs? And it is. It runs from pi down to 0 here. And so pi radians, or 180 degrees, is an acceptable output here. Next up, in this one, we solve for the missing angle. So we have two sides of our triangle. We don't know the angle. With respect to this angle, 12 is the hypotenuse and 9 is the adjacent side. So we have adjacent and hypotenuse. So this is a cosine situation. Know that the cosine of the angle will be the adjacent over the hypotenuse. So then we ask ourselves, which angle has a cosine of 9/12? I'll have us use our calculator on this one and take the cosine inverse of both sides. That would be our angle theta then is cosine inverse of 9/12, or 3/4, and that gives us 41 degrees and 25 minutes. Of course, when you do cosine inverse, it's going to give you a decimal, something like 41 point and so on. Then you would take away the 41 and multiply it by 60 degrees in order to get this 25 minutes part. By the way, if your calculator happened to be in radians, then you would end up with approximately 0.7 227 radians, which would be something a little less than pi over 4. After all, 45 degrees would be pi over 4 radians, and so this would be a little less than pi over 4. Our next topic is the composition of trig functions. When you have a composition of trig functions, we'll do one trig function, take the output, and then plug it into another trig function. Alright, so for this first one, the cosine of 13 pi over 6, we'll do that one, since it's inside the brackets, take its output, and then enter it into the sine inverse function. We also notice that it says evaluate this function on the interval of 0 to 2 pi, meaning that our final answer needs to be an angle at least 0 radians and less than 2 pi radians, or less than 360 degrees. So let's start by working on the inside and then working out. Cosine of 13 pi over 6. So this 13 pi over 6 is not an angle that we see often. It is an angle that's more than 2 pi. In fact, it's 2 1/6 pi. Now normally our standard circle only goes up to 2 pi. So think about it this way. We would go starting, of course, at our initial side in standard position. We would go 90 degrees, 180 degrees, which is pi radians, and 270, 360, which is 2 pi radians. And then we need to go another 6th pi, or pi over 6, past. So essentially this is another pi over 6 past. Now pi over 6, or 1/6 pi, is the same as 30 degrees. So what we have going on here is a 30-degree angle inside that triangle here. 30 degrees here, making that 60, and at a right angle. So we've got a 30-69 triangle going on. That means this is 1, root 3, and 2. Now let's take the cosine of this angle. So the cosine is x over r, root 3 over 2. And so the output is going to be root 3 over 2. Now we ask ourselves, what is the sine inverse of root 3 over 2? So which angle has this for the sine value? So we can draw a triangle to make things a little clearer. Opposite over hypotenuse, or y over r. This then would be a 1, root 3, 2 triangle. 60 degrees goes across from the root 3. And so this would be 60 degrees, which in radians is pi over 3. Next one. Find an exact value for the sine of the cosine inverse of 4/5. When we do a cosine or any trig value inverse, the output will be an angle. So which angle has a cosine of 4/5? Cosine is x over r, so x will be 4, and r will be 5. And so what is this angle here? Well, this isn't one of those standard 45, 45, 90 or 30, 60, 90 triangles. All right, let me pause here just for a moment because it's time for another class to come in. All right, continuing on. if we use the Pythagorean theorem, we can figure out what this side length is. If we did a squared plus b squared equals c squared and solved, we would see that that side is a length of 3. So then, the cosine inverse of 4/5 will be the angle which has a cosine of 4/5. There's a couple ways you could do this. First one, you can plug cosine inverse of 4/5 into your calculator. You're going to get something, if your calculator is in degrees, like 36.8699 degrees. Then if you do the sine, yikes, if you do the sine of that, that's still a mess, sorry about that, you'll end up with an output of 0.6 exactly. Now that seems like a really convenient number when you enter it into a messy decimal. Here's the reason for it. At the beginning of the problem, you did the cosine inverse of 4/5, and so it gave you an output of an angle, which is this angle right here. So essentially then we're asking, what is the sine of that angle? Well, the sine was going to be opposite over hypotenuse. 3/5, which has a decimal, equals 0.6. Last two. Find an exact value for this expression. Let's start by drawing an angle with a tangent of 7/4. So y over x, 7/4. Do the Pythagorean theorem. 7 squared plus x. Come on, Microsoft Word, you can do better than this. 7 squared plus 4 squared equals the hypotenuse squared. Just call that r squared. Add these two together, square root them, you'll end up with the square root of 65 as this hypotenuse. So then the tangent inverse will be the angle which has this 7/4 is the tangent. So then that's going to be this particular angle right here. You could plug this into your calculator, tangent inverse of 7/4, and then take that number and then plug it into the sine function. Or what you can do is say that this expression here will be a particular angle. And that's going to be the angle which has this tangent. So we've just drawn the triangle which has that angle as a tangent. So then we want to know, what is the sine of that angle? So the sine of this angle will be y over r, which is going to be 7/√65. Rationalize the denominator, we'll multiply that by √65. Yikes, √65 over √65. And that's going to give us 7√65 all over 65. Last one. So this one has 3 trig functions in it. So first off, the arctangent of 1. We ask ourselves, which angle has a tangent of 1? Y over x, this would be a 45-degree angle right here. So that would be a 45-degree angle, or pi over 4 radians. And then which angle has a tangent of -1? So this would be -1 over 1. You could say that that would be this angle right here. -1 for our y over our x. So this would be a -45-degree angle right there. So this would be 45 degrees minus -45 degrees. Let's pick this one up in the next video, and I'm going to clean up that mess. and then we'll wrap this problem up.